All right, well, in this third part of the data structure series, I'd like to talk a little bit about two-dimensional data structures. This is something that we might not necessarily need right away in the class, but as soon as you move outside the class and start working on real-world data, you will find the need for some more complicated data containers. So I'd just like to spend a little bit of time talking about this and show you one example. This is a real data from a research project in London. They went to parish churches in East London and were recording data out of the church registers. I downloaded that, and this is a subset of that data. This is the age of parenthood. And so somewhere in East London in 1573, there was a father whose child was baptized or christened, and he was 26.3 years old at that time. I have a similar spreadsheet for women, exactly the same thing. It's just a 2-column spreadsheet, the year and then the age of a parent. So as we know, we can't just bring data into a Python program. We have to prep a container for it. So the question would be, well, what kind of data container would we use if this is the data set that we want to work with? Well, we've got a couple of clues here. Again, this is just a screenshot from my spreadsheet, but if I look down the rows, there's a little bit of metadata there, and those look suspiciously like list indexes, don't they? Sure, the spreadsheet starts at 1. Python would start at 0, wouldn't it? Of course, because we would have that joke, where do list indexes start? And everybody else uses 0. So it's possible that this could be a list, right? That we could have every row goes into just a drawer in a list element. They're all numerically indexed, right? Here there's a header row, and that it doesn't matter. We can avoid that. That's not a problem. So my first thought, incorrect thought is that this looks like a list. And so I could frame this out in Python as a list, right? Remember, my square brackets always signify a list, and there's going to be a certain number of elements there that are going on the inside. So the next question is, great, what are those elements? What should that thing look like? Well, if I just took those by themselves, it looks suspiciously like a dictionary, doesn't it? You know, there are key value pairs. The year here is 1573. The age of that particular parent in 1573 was 26.3. Yeah, that's right. 26.3 years old. So it looks like a key value pair. Now, if I didn't do anything else, if I just wanted that in Python, I would write that like this. Curly brackets signify a dictionary. The key is year. The value is 1573. The key is age. The value is 26.3. Terrific. So, to me, this looks like an interesting combination of lists and dictionaries. Well, let's go back and just review this slide for just a second, because I have to fess up here. I was a little dodgy with you, and I kind of want to come clean right now. So, lists have these properties, right? Any number of drawers. The drawers are always in the same order. The drawer has a label and it's a number. They start at 0, etc., etc., etc. But where I was a little dodgy is in the second one, that every drawer contains either 0 things or 1 thing. You may have interpreted that as it needs to have a scalar, like a string or a number, but that's not true. What if that one thing was a little tiny dictionary? And that is fine. So what I would have is, metaphorically, a filing cabinet, and every drawer has a numeric label called an index. But every time I open the drawer and I look inside, there's a little tiny dictionary in the drawer. That is exactly the data structure that I want to build. So if I started to frame it out, it would probably look a little bit like this, right? So I've got men. I would have the same thing for women as a different data set. The overall structure is a list, so I start with square brackets as a way to signify what that data structure is. Every element here, however, is not a scalar, but is in fact one of those little dictionaries. So as I start to frame it out, it's going to look more like this. So I have 3 in this version. Obviously in the spreadsheet it's going to be much, much, much bigger. But in this version, my list really only has 3 elements. I don't care how they get indexed. Python is going to do that automatically. So it's going to index them as 0 and 1 and 2. But the values are going to be little dictionaries. So if I extract the 1th element from men, I will not get a scalar, but in fact, Python will actually give me this little tiny dictionary, a little 2-element dictionary, which is perfect. And I can go further now to access any, what we would call in the spreadsheet, a cell. I can just list 2 indexes. I can list an index and then a key. I just put them side by side, no spaces in between them, and I can pull out any individual element. So of course here, this is the 0th row of men. Right? In my spreadsheet there on the left, that's kind of row 2, but that's okay. Just don't worry about it. So in the 0th row of men, the column called year is going to deliver to me the number 1573, which is the year. And if I wanted to go to, say, the 2th row of men, that's going to be row 4 over there. But I go to the age column, I'm going to get 29.6. So I can actually pull out any combination of these. I can look at a 1 row. I can pull out individual cells. I can go through, as we'll see in the next slideshow series, I could actually go through every single row in here, and I could open up every single drawer. I could open up the drawer of that little tiny dictionary, and I could find out, like, what is the average age of parenthood in my entire data set. I could calculate that. I could filter my data too, so I could say, well, look, I'm only interested to find out the average age of parenthood from, say, 1585 to 1610 or something like that. So I could write some code to open every single drawer in my list. I could check the year to make sure that it fulfills my criteria. If it does, I will save the age, and I will just add those up. At the end, I will count how many I happen to have, and then I can calculate the average pretty quickly. So let's just flip over to the terminal window, and we'll just play with this for a second. All right, once again, here we are back in the terminal window, and I'm just going to, again, as always, jump into the Python interpreter. I've already taken the liberty to type out that little list of dictionaries, and so I'm just going to paste it here. This is the same thing that we just saw a second ago in the slideshow. And again, just to repeat, you'll notice because it's a multi-line item, Python knows that I open with a square bracket, and it's waiting for that closing square bracket, but because it hasn't seen it yet, I get this second line prompt of the ... But if I ask it what men is, you'll see that I have here exactly the data structure that I just put in. It maybe isn't quite as neat and tidy and pretty right now, but you can see it is in fact a list of dictionaries. So if I ask for that 1th element, you can see exactly what I get. I get that little tiny dictionary. And if I wanted to look inside that little tiny dictionary, all I need to do is add a key to look through that dictionary. And so the year in the 1st row is 1575. But similarly, I could look at age. I'm just going to be a little bit lazy here and type it like that. So in the 2th row, 0, 1, 2, if I drop over to the age column, that one is 29.6. So this is a terrific way to start to work with these multidimensional data structures. So 2 things. Number 1, it doesn't have to be a list of dictionaries. It could be dictionaries with lists inside of them or lists with lists inside of them. It doesn't really matter. Python couldn't care less how we arrange that. But the other thing is you probably have already thought about this, which is that this data structure is a list. Inside the list, we have a dictionary. The dictionary could itself contain a list, and that list might contain another list, and that list could contain a dictionary. So it's almost like an infinite hall of mirrors. I could be turtles all the way down here. It could be lists all the way down. I can nest these kinds of data structures inside each other as far as I want to go. Python isn't really ever going to get confused about this. In fact, I will get confused about it much faster than Python will. But this is the strategy that we use anytime that we have really, really complicated data in the real world. We will find really quickly that the data of the real world escapes simple buckets in simple lists and simple dictionaries. And so we need to start to put together those elemental data structures into bigger composite kinds of data structures. So sometimes we call, these scalar variables buckets and then, lists, sets, tuples, dictionaries. We call those sometimes built-in data structures because they're sort of like the most primitive, the most basic, the most fundamental data structures that the language gives us. And out of those fundamental basic data structures, we can build really elaborate, really baroque, very expressive data containers that capture all the complexity of the real world for our projects. All right, well, that's it. This last one was very short and sweet. The longer we go, the shorter it gets, I guess. That's it for the data structures one. And we'll move on to some of what we think of now as logic structures or some of the other control structures in Python. Thanks.